Good morning, everyone. Thank you for coming to my presentation today. My name is Mitsuharu Ito from Fujitsu Computer Technologies. Today, I'd like to talk to you about Linux file system analysis for IVI systems. I like football very much, both watching and playing. As you all know, the world's largest football tournament is being held now in Brazil. In actual football matches, many kinds of embedded devices are used. For example, high-definition video transmission system, goal decision system, even offside signal transmission devices on assistant referees' flags. The device on the right side is Fujitsu IP9500, the real-time high-definition video transmission device used in South Africa 2010 to broadcast football matches to Japan. Inside those devices, a large amount of data are stored as files on file systems, such as videos, sounds, and sensing data. And various types of embedded devices have been used more and more, not only in sports, but also healthcare, agriculture, and also automotive industry. In order to handle the dramatically increasing big data efficiently, the core technology of file systems will be more important. Okay, here is the agenda of my presentation. Firstly, I'll explain the background, introducing myself and explaining the motivation of this work. Secondly, I'm going to give details of automotive Linux requirements of file systems and functional suitability of some typical types of file systems for the requirements. Then I'll explain some evaluation methods and share the results we obtained. Finally, I'll summarize our conclusions. First, let me introduce myself. I work at Fujitsu Computer Technologies as an embedded software engineer. I've been involved in developing embedded Linux distributions and device drivers. Our distribution is used for server system controller, network equipment, printer, IVI, and many other devices. So we are familiar with wide variety of embedded systems. And what is file system? As you know, it's one of the features of operating systems to store and organize data as files on media, such as hard drives, optical media, and flash drives. Linux supports many kinds of file systems. Each file system has various characteristics which are designed to optimize for their targeting systems and recording media. In IVI systems, there are a lot of types of data, such as 2D, 3D maps, videos, sounds, information about traffic, shops, disaster, sensing data, and system logs. And I'm going to explain our motivation. Why did we start this work? AGL requirements definition version 1 is planned to be released soon. The document includes a section about robust file system and references to some types of file systems such as BARFS, ext234, VFAT, and UFS. And Fujitsu has been contributing to BARFS from an earlier time of its development. We are number 2 contributor to BARFS as shown in this GitLab website. Then there were some questions. How suitable are BARFS and other file systems for IVI? How about functional requirements and non-functional requirements? And what is necessary to make file systems more suitable for IVI? So we started our study, file system suitability analysis for IVI systems. Then let's move on to the main subject, file system comparison for IVI. Here is the AGL software architecture diagram. It's composed of 5 layers from top side: application, human-machine interface layer, application framework layer, open source middleware layer, automotive specific middleware layer, and Linux kernel and device driver layer. The block of file system named robust file system is here in kernel and driver layer. I can't describe each layers and blocks in this limited time, but I'm going to focus on details of file systems. Now let's take a look at the requirements of file systems. This slide shows priority 1 mandatory requirements of file systems. They are categorized into 3 groups by the type of media. Group number 1 for SSD, eMMC. Number 2 for raw, NOR, and NAND flash memory. And group number 3 for USB stick, SD card. I made the embedded system specific requirements into bold font, such as power failure tolerance, quick recovery after power loss, and error handling on raw flash memories. According to the document, all of the requirements are functional requirements. And this slide shows priority 2 optional requirements of file systems. They are also categorized into 3, and all of them are functional requirements, just like priority 1. In particular, compression support is sometimes needed for embedded systems due to the restricted resources. This table shows how much the file systems meet the priority 1 mandatory requirements. As listed above, there are 6 types of file systems: ButterFS, ext2, 3, 4, VFAT, and UFS. These file systems are described in the document as reference implementations of robust file systems. We translated the relationships to reference into check mark on this table, and filled the blanks with results of our own research. Number of check marks indicates that the most suitable candidates for SSD or eMMC are ButterFS and ext3.4 with 7 checks. Number of check marks of group 3 means ButterFS and ext3.4 are also suitable for removable devices. And I focused on the group number 1 because nowadays eMMC and SSD are mainly used in the embedded devices to store important data. And among this group, we regarded power failure tolerance as one of the most important requirements for IVI, because the power failure has the highest risk for the integrity of the file systems. Okay, to recap on the AGL requirements of file systems, ButterFS and ext3.4 are most suitable candidates for mainly used eMMC SSD. ButterFS and ext3.4 are also available for USB stick SD card. And ext4 is successor to ext3, so we focused on ButterFS and ext4 as the target of evaluation. And among the mandatory and functional requirements, we focused on the power failure tolerance. We decided to evaluate this requirement. Now let me describe the other requirements of file systems. There are some important requirements except for robustness. Short boot time. It's time to show splash screen or home screen on the monitor or play start sounds within a few seconds in most cases. As performance, I/O throughput and application QoS are required. QoS means the constant performance under high load, not to keep HMI applications waiting for a long time. In other words, comfortable operability is required. Security and scalability. We focused on short boot time and performance as requirements to be measured, so we decided to add them to our evaluation list. Then, I'd like to talk about the overview of ext4. ext4 is a journaling file system developed as the successor to ext3. It was merged in mainline kernel 2.6.19 in November 2006. Its key features are large volume and file size support, journaling and journal checksum, persistent pre-allocation, and so on. ext4 is used as standard file system for many major Linux distributions: Fedora, Red Hat, Enterprise Linux, Ubuntu, and Debian. Here is development status of ext4. ext4 has been used a long time from ext2, so it's mature enough. The graph below shows the changes in the total number of patches. It's the total of the fixed or bug patches plus the other patches. As you can see, for recent few years, the number of patches gradually fell less than 400 patches. And the principal developer of ext3.4, Mr. Theodore So, stated that although ext4 has improved features, it is not a major advance. It uses old technology and it's a stopgap. And he believes that ButterFS is the better direction because it offers improvements in scalability, reliability, and ease of management. Then let's take a look at the overview of ButterFS. ButterFS is a file system aimed at implementing advanced features while focusing on fault tolerance, repair, and easy administration. Its development began at Oracle in 2007 and merged in mainline kernel 2.6.29 in January 2009. The key features of ButterFS are B-tree data structures, copy on write mechanism. It logs all data and metadata and offers data consistency and easy snapshots. Writable and read-only snapshots, transparent compression, RAID, and so on. Here are supporting distributions. MeeGo as standard file system since 2010. OpenSUSE 13.2 using ButterFS by default but will be released in November. Oracle Linux since 2012. And Red Hat Enterprise Linux 7 as a technical preview, so ButterFS may be supported by the next version of RHEL. It means that ButterFS has been supported by major distributions and will be used more and more. And Mr. Chris Mason, the leading developer of ButterFS, said Facebook uses ButterFS on their web server. How many of you have Facebook account? Thank you, and congratulations, you are already ButterFS users. Okay. Here's development status of ButterFS. some advanced features are under development. This graph shows the changes in the number of patches. The bars mean the total of the fixed or bug patches and the other patches. Red line means total patches of ext4, and orange line means Fujitsu's patches for BADFS. For recent few years, the development of BADFS has been very active with around 800 patches. It's twice as many patches as ext4. Okay. Now let's move on to the evaluation. As I mentioned so far, we conducted the evaluation as listed here. We evaluated characteristic requirements for IVI, and the target file systems were BADFS and ext4. So we carried out the 3 types of evaluation as robustness, power failure tolerance, as boot up time, file system mount time, as performance, file I/O throughput under normal and high load conditions. First evaluation, robustness. We evaluated the tolerance to unexpected power failure while writing some data to files. Here's the environment. Freescale's tower board, which has 500 MHz ARM Cortex-A5 processor, 1 GB memory, and 60 GB micro SD card. The software was Yocto-based Fujitsu in-house distribution with kernel 3.15 RC7. And we used these tools. Our self-made power supply control unit that periodically turns on and off the DC power supply every minute. And simple file writing application that continuously creates 4 KB files and writes to it. Here's the results. Over 1,000 times of power failure were generated to both BADFS and ext4. As a result, with BADFS, no abnormal situation occurred. In contrast, with ext4, corrupted inode had gradually increased up to 32,000 and finally fell into a normal disk-full state, and the application couldn't write any data. The copy-on-write mechanism of BADFS showed very strong power failure tolerance. The output of df command showed 100% disk usage for ext4, though actual disk usage was 2%. And it took 3 minutes to finish file system check and recovered to normal state. It may be a big problem for boot time requirements. The second evaluation, boot up time. We evaluated the time length of file system mount. However, this time we measured mount time after boot sequence was completed in order to measure real mount time, excluding the inference from other tasks. We used Freescale's board and the Fujitsu in-house distro with kernel 3.15.1. They are almost the same as version number 1. And we customized the kernel to record timestamps at start and end point of Mari process. The number of files is strongly related to mount time. So we prepared 3 types of file systems, 4,000, 70,000, and 1 million files each. Here's the result. The x-axis is in microsecond time. This graph indicates that ext4 was mounted twice or 3 times faster than BADFS. The reason of this may be that ButterFS has dynamic inode allocation mechanism, and it took a long time to collect inode data spreading through the drive, unlike x84. However, the dynamic inode allocation allows a limited number of files. In contrast, x84 stores inode data in a fixed area, but x84 has a limit of max number of files. All these mount time are under 250 microseconds, so it seems to me that this mount time may have tiny impact on a few seconds requirements to boot up time. Considering the whole boot up time with these results, the time for initially reading programs and data has more influence than the mount time. The last evaluation, performance. We measured basic file I/O throughput and throughput under high load. Here's the environment. Intel desktop code, which has 1.66 gigahertz dual-core Atom processor. It's 4 cores with hyper-threading, 1 gigabyte memory and 32 gigabyte SSD. The software was Fedora 20 with kernel 3.15.1. And we used FIO to benchmark the throughput and to make high load condition with ES command for user space load. And conditions, single and multiple FIO running. FIO makes one large file, 2 gigabytes for read, 1 gigabyte for write, and reads from and writes to the same file with small block size to simulate database-like behavior. And some combinations of throughput-related mount options. Here's the result of I/O throughput benchmark with single I/O, low load. Read on the left side and write on the right side. Sequential I/O on the upper side and random I/O on the lower side. In terms of read, ButterFS was slightly faster than ext4, and some options related to compression and SSD awareness were effective. For this use case, no compression was better than any compressions. However, according to some reports on a certain website, enabling compression options was better than no compression for high-spec CPUs. And for random I/O, the results were reversed. In terms of write, ext4 was almost twice faster than ButterFS. The reason can be that ButterFS has copy-on-write mechanism, and it copies the whole file before writing, even if the writing size is small. So copy-on-write doesn't fit for this kind of writing. Each file systems have advantages and disadvantages. So we can see the different results with other use cases. In fact, on the Phoronix.com, the famous website for countless benchmark data of computer systems, one of their benchmark results shows that ButterFS was the overall winner. And here's the results of I/O throughput benchmark under high load. The positions of read, write, sequential, and random are the same as the previous slide. And in order from the top, the 4 sets of bars mean ButterFS under low load, high load, ext4 under low load, high load. In terms of ext4, every I/O throughput decreased significantly under high load. In contrast, decreased ratio of throughput of ButterFS is less than ext4. The reason may be that ButterFS made 19 kernel threads and they used CPU resource effectively. Now let me conclude my presentation. In terms of suitability for AGL requirements, ext4 and ButterFS are most suitable file system from functional aspect. But it seems to be necessary to evaluate the other file systems such as XFS, NeoFS2, which are not referenced from AGL requirements definition. And this table shows the score of file grade evaluation under some specific environment and conditions like this study. It's my understanding that for power failure tolerance, ButterFS was extremely excellent. For one time, ext4 was a little better than ButterFS. And for I/O throughput, ext4 was better than ButterFS. In math options, there were some differences regarding compression and SSD awareness like this. Again, as I explained earlier, each file system has advantages and disadvantages. So I think that more evaluations will also be needed for IVI systems openly, like Phonics.com. Finally, let me talk about future. Forecasting the future, hardware specs will be more rich in the whole IT industry. So the priority of requirements may change, such as CPU memory usage, compression, dwell time. And the development of EVs and FCVs may cause a change for requirements of file systems. For instance, power failures may almost never occur on EVs or FCVs. So we have to adapt file systems to these changes flexibly and rapidly. Okay, Fujitsu will continue to improve ButterFS from now on too. Let's use and evaluate ButterFS with various requirements, environments, and conditions to make ButterFS more suitable for IVI.